Hi. So, all right, I understand. I graded some over the weekend. I'm going to install them this week. I graded your exams also. So, we'll talk about that on Wednesday. All right. So, I want you to focus on what I am teaching you, because the mechanisms are very important. And as you can see, mechanisms is what tells you what's going to happen in the reaction. So you will have mechanisms on all exams for the rest of this semester and all of next semester. So please pay close attention to the mechanisms.
I have a question.
Yes, John.
It's not really related to the rest of the class, but say I only took organic chem 1.
Mm-hmm.
Does MCAT go over anything on organic chem 2?
Yes.
Some people have said
Goes on both.
It does. Okay.
Yeah.
So see your organic chem 2 then.
MCAT will cover organic 1 and organic 2.
Because some people said take biochem instead of the second organic.
You should take both.
Okay.
Biochem is very important now in MCAT. It used to be less, and now it's more. I don't know if there's PCAT on there. I don't think there is. There's more organic and biochem. Yes. Yeah. Yes.
What's the name of the chapter?
Chapter 10.
But the official name. The name of the chapter.
Uh-oh, what's going on here? How did it just do that?
Yeah. It's the free radical. Is someone crying?
How did it just do that?
It's me. It's my internal child.
Chapter 10?
That's my conscience.
Oh my gosh, what is going on?
Oh, it's almost Halloween. Oh, I don't know.
As soon as I touch the screen, it disappears. Why?
Uh-oh.
Done. Done. I think something's loose.
I just recorded it.
And I like that before. Check the import terminal. Yeah. Go, Karen, go. Don't fall. Don't look.
I'm having a
Your knee pop? Yeah. No, that was my head. That was my heart.
Yeah. And it seemed like I fixed it, but it's not working right.
I don't want to break it. Well, because the thing I said is there's something with that one.
Yeah,
that one that you're touching
I
right
think
now.
the screws.
Yeah, and screws on it.
But I don't pull it.
There is a very
I
tight,
don't have good luck.
there's a very
You're
tight
kind of upset
one
by
right
going
here
all the way freaking here.
that keeps,
Hey, you want to go in and out?
that I just,
No, I'm
Go in and out.
Actually, yes.
It's working.
There.
this one was moved over and that was like pulled over really tight and it was broken. So I just loosened it up a little bit here.
All right, let's take a look. Thank you. Let's see.
Uh-oh.
Maybe it's the wire.
I just reported it now, so
Could be the wire.
this is bad.
So now, what about the online people? Are they gone?
They're gonna be,
I picked a
they're,
good day to come here
I
then.
don't like doing the online stuff.
Can we restart the projector?
Oh my God, what's happening?
it's not the projector, it's the computer.
Then I tell him it's not working. He never checked his email.
I know.
Yeah, he never replied to me.
Never replied to me either. I
So
tried
it has
that.
nothing to do, has nothing to do with,
Last
because I mean, I'm wiggling wires right
Yeah,
now.
don't even bother telling me.
All right, let's see if this will work now. Intro to free radicals. Anyone know what a free radical is?
We did that. It's like one electron.
So let's discuss what is a free radical. You've already learned reactions with the nucleophile and electrophile that have 2 electrons moving. Remember? 2 electrons move. So if we have a reaction, let's see how this is going to be. This is not good at all.
See, it's pointing to like that wire that like Karen was trying to like.
As soon as I touch the screen on the computer, it turns off.
Well, because the connection is not good.
It's a broken wire, I think. We should just disconnect it and pull it through the ceiling.
Well, I'm not allowed to do any of those fancy things.
Well, you don't have to do it.
Here they are.
Justin, we need your help big time, please. As soon as I touch the screen with this, it all turns off. There it is. I had reported it last week, but I need you to see what can go on. And it totally logs me out, and then I have to log back in.
That's weird. Okay, can you log in for me?
From here? I like it.
It's been working beforehand.
No, it has not been working. I've been working it with the mouse. It works fine, but as soon as I do touch screen with the pen, it turns off.
Okay. That is weird. I'm gonna clear this if you don't
Go
mind.
ahead. Turn off the recording there.
Oh, okay.
Yeah.
It's like it disconnects. Nah, can you log in for me again? It's something with the software. Because it does it when you touch the screen at all with anything.
To log in again.
Yeah. What time's your class over?
Yeah, 4.
Okay. Works like that.
Yeah, with the mouse it works fine, but with the pen, it's gone.
Even with the mouse though.
Okay. One more time.
Are you sure?
Yeah, I don't know what. I'll probably have to uninstall and reinstall your software for it. That's weird. Let's see who works if I run it as admin.
Yeah, let's see.
Nope.
Administrator doesn't work, huh?
Mm-mm.
All right, is there another room I can go to with all of these programs installed, ready to go right now?
I don't know if there's anything in 800 right now that's open or not.
Go now? We have Starbucks?
Okay, yeah.
Starbucks has Wi-Fi.
We might have to If you draw with the mouse until the end of your class, I could probably come back down and reinstall everything.
It's impossible.
Yeah.
I need to go.
Okay. I don't know where else.
I can write in words, but to draw with a mouse is gonna be hard.
Yeah, because it's a software issue, which I don't know why all of a sudden, you know. So last week and then the week before that it was fine.
Yeah, but last week I put a ticket in to say there was a problem with it. It wasn't even turning on.
Okay.
Thursday, I think Thursday.
So okay, because in the ticket we thought that you just meant the monitor wasn't turning on, so we didn't even look at the.
Yeah, but no, this is new.
Okay.
This problem is brand new. But
So
before
today-
the monitor wasn't even turning on.
Okay. Yeah, because everything in the settings looks fine.
Can I lecture and it see on the board?
What do you
How
mean?
can I lecture and videotape it on the board?
The same way for Zoom. You have to use Zoom.
Okay. Can this see the whole board?
Oh, so you're wanting to like draw on the.
I'm
Okay.
gonna draw on this board right here.
I can check and see if 401 is open.
Let's do it.
Okay. Okay. I'll let you know. What's the phone number for this room?
I have no clue. Call me on my cell phone.
Okay, what's your cell phone number?
714.
714.
326 5907.
Like if I go somewhere out of service, my
Anthony.
phone's wrong, and like I'll be
Okay.
smack in the middle of the town.
What room is it?
400. I'll go look and see if it's
Where
open.
is 400?
Past 500 up there. It's the one on the hill.
Oh, yeah.
Yeah.
I think that's where I learned with Jordan.
Okay. Oh, it will.
We need to go now. 'Cause it's already gonna be half an hour wasted here.
Okay.
I had the iPhone.
Let me. I'll see what room I can move you.
I had the iPhone 6 like, before I got my Galaxy Phone and like my iPhone 6 like my bed. I had like 2 pictures, like 5 apps, and like 130 songs, and like it was like no storage on your memory. Find more memory. And I was like, no, yeah, my memory's fine. Pictures, memory's fine. The thing is like my battery, and I'll just shut off on me sometimes. So like I tried my phone at night. Yeah, I tried my phone at night before I go. Dude, I got my phone this big.
I have the 7. And the 7 is perfect. And then like all the 10s around, and I'm like, I just
I got rid of the home button. Yeah, you have to like swipe up to go home now. I know, I love my home button. I love my home button.
watch me get the 10 in like 5 years from now. Because they're gonna like keep updating, right?
Yeah.
Like, okay,
I hear they're finally coming out with the 9. They went from like 7, 8, 10, like 10 Max,
wait, when's the
10
9?
S, like, and then I think they're going to the 9. They've added numbers.
I just got 9. I'm fine.
So I added like so my phone, I'll turn it to like 100. I remember when the iPhone 3 came out. I was like,
Everyone went.
Resume recording. Good. All right. Chapter 10, Intro to Free Radicals. How many of you know what a free radical is? Oh, it's all reversed. That's not good. Yeah,
You gotta learn
everything.
how to write backwards.
I can't.
cool, rat.
Intro to free. I know. I have to. So I'm not going to write words. I'm just going to say it in words. And I'm going to draw structures, which you should be able to see forwards or backwards.
Oh, sounds good.
But we can see it just fine though.
Are you sure? I can't even see a thing apart from.
Oh no, I think he's saying like it's backwards. I don't see it backwards.
It's not backwards.
Oh, it's
No,
not?
Reverse.
No, it's not.
Can you?
Oh, it's forwards?
Yeah, I can see it. I mean, I can read
What I
it.
see is backwards.
Oh, just a
Okay.
blur though.
All right.
just blurs.
I mean, it's a little blurry, but that's about it.
From our reactions that we have learned already for SN1, SN2, E1, E2, they all utilize 2 electrons. And when we draw the arrow from the electrons, we always draw a complete arrowhead, and those 2 electrons are on the arrowhead. This is for an ionic reaction. Ionic reaction always has a movement of 2 electrons. But a free radical reaction only has 1 electron. And when we have 1 electron, we have a fishhook arrow, like this. This is the difference between ionic and free radical reaction. This section, or this chapter, is dedicated to free radicals and is the only chapter in organic chemistry that you're going to learn when you take Chem 235 and 236 that only utilizes 1 electron transfer. All the other reactions that we're going to learn in organic are with 2 electron transfers. Yes, Natalie?
Why do we skip from chapter 5 to chapter 10?
The way that the author has put these chapters in the book, I want them so you understand them sequentially and understand organic chemistry better. If we follow the way that the author put them in the book, it's going to be all random and you're never going to understand them in a logical format that's easy for you to understand. I'm trying to make it easy for you to understand. All right? Because there's a lot of chapters in the first 12 that are for organic chemistry's second semester organic. You don't even learn them first organic. So I have to pull the chapters from different sections in the book and organize them so you understand them better. Yep. Yeah. All right. So let's understand. Does everyone understand if we have an ionic reaction versus if we have a free radical reaction?
Yeah.
Okay. I want you to understand another thing. Oxygen, elemental oxygen that we breathe in every breath, is a diradical. This is the way it should be written. In General Chem, they teach you oxygen like this. And this is the wrong structure. The reason why this is the wrong structure is because when you open up a banana, what color does it turn if you don't eat it?
Brown.
Turns brown. How about if you open an avocado and you don't eat it? What color does it turn?
Brown.
Turns brown. How about if you open chips and you don't eat it and let it sit out from a party overnight?
Stale.
They become stale. How about nuts that are opened and that you don't eat, and then you go to eat them or smell them? What do they smell like?
Not
good.
Rancid.
I still eat them.
You don't want to eat them.
They get stale.
So oxygen, since it's a radical, it's a diradical. Di means 2 radicals. 1, 2. Oxygen reacts with everything. This is the problem we have aging. This is why we age, because of this molecule right here. All right? We need it to live, but it also kills us. All right? So let's do some reactions and understand about free radical reactions. And how many of you have heard of antioxidants before? In foods, in berries, or in colored fruits or colored vegetables? You're right. So antioxidants provide a hydrogen or 2 hydrogens to this free radical and neutralize it, like vitamin C, vitamin E. So free radicals are generated in your body because oxygen is converted to carbon dioxide. So let's understand. The 2 halogens we're going to be understanding in free radical reactions are chlorine and bromine. These are the two halogens we're going to be dealing with. They both have this favored ability to react with these type of carbons. Tertiary is greater than secondary. Secondary is greater than primary. What I mean by that is if we take chlorine, we can react it with a tertiary, a secondary, or a primary. Same thing with bromine. It can attack to a tertiary, secondary, or primary. But the ratios are different for both of these. And let's follow what your book says for these ratios. Let me see here. Here it is. Relative rate. So this is a relative rate. Let's put here relative. The relative rate, this is for chlorination, is, let's put these in different color, 5.2 to 3.9 to 1. That's for chlorination. And for bromination, so we get this type of a ratio. So the problem with chlorine is it can go to every position on a molecule, whereas with bromination, it prefers the most substituted tertiary. So what we call this is chlorine is not selective. Not selective. And bromine is selective. Bromine is selective, chlorine is not selective. All right, everyone understands this? Any questions so far? Did you copy everything? Can I erase? All right.
Yes.
All right, good. Now, with free radical reactions, let's understand what's going to happen here. Free radical reactions, let's say if we take chlorine, here's elemental chlorine gas. If we take chlorine or if we take bromine and we had here, if we add ultraviolet light, H mu, or if we add heat to this, light or heat breaks apart the bond between both chlorines or both bromines. Let's look to see what's going to happen. When we get this to react, look what we make. We make radicals of chlorine. This type of reaction is called a...
Mr. Hollow,
Yes, sir.
on top of your arrow there, you have HV. What does that stand for again?
H mu. So in physics, you learn H, and then you have a mu, mu, which is like a V. It looks like a velocity, but it's the sign for velocity, and they pronounce it mu.
It's velocity.
Mu is this type of a symbol. All right. Okay, hold on a second. Hello? Okay, is that cool?
Yes, sir.
So it just means ultraviolet light. Justin? Excuse me? That's okay. I'm already lecturing in here and I'm just doing it from the board and I'm using the camera that's mounted onto the touchscreen. It's fine. Okay, well, after I'm done here, please come and play with this one. If you want me to put another ticket in, I will. Okay, thank you. All right, let's continue. So this H mu means ultraviolet light. All right. So when we see a bond that breaks like this, we call this heterolytic cleavage. Hetero means it splits. One electron goes one way, the other electron goes the other way. Heterolytic cleavage. Now, when we were doing reactions with SN1, SN2, E1, and E2, 2 electrons moved with the leaving group. You remember that? So let's take a look at this. If we did SN1 reaction, let's see if we had this. If this is SN1, when we did the reaction for SN1, 2 electrons moved that were in the bond, and now they're going to the bromine.
Both of them?
Yes, 2 of them. 2 electrons are moving to the bromine, not 1. So we get this type of a reaction. When 2 electrons move, we call this homolytic. Excuse me, I need to split this. This should be homo. Let's reword this. Homolytic should be for free radical. Homolytic is for free radical. Heterolytic is for ionic.
So when
So I had them reversed, I'm sorry.
so when the thing breaks, that means it's homolytic?
Yeah, so let's go through this again, because I made a mistake on the naming. When both electrons, one electron goes to one atom and the other electron goes to the other atom, they are equally being split apart. One goes one way, the other goes the other way. We call it homolytic cleavage. When 2 electrons break from the bond, that's ionic, like SN1, SN2, E1, E2, all the reactions we learned. 2 electrons move, We call this heterolytic. All the electrons go one direction. None of them are kept the other side. They all go one way. That's what we call heterolytic.
So hetero doesn't mean split.
No.
Homo.
Homo means to split. Homo means to split. Hetero means to move, all move in one direction. I hope that can be read. Maybe we need to rewrite it. All move in one direction.
Okay, so we're backwards then.
All move in one direction.
So radicals will be homolytic cleavage then.
Free radicals are homolytic. I made the mistake and I told them heterolytic. It's not. It's homolytic.
And then ionic, you'll have heterolytic.
Correct.
Which is homophosis.
That's correct. So this is, we look over here. This is free radical. This is ionic. So ionic is heterolytic cleavage. Free radical is homolytic cleavage. Does everyone understand that?
Yes, sir.
All right. Let's continue.
So those chlorines, they're not positively, or they're not.
No charge on the chlorines because they have the amount of electrons around them from the periodic table. They're neutral. Correct. They're neutral. Any questions before I erase? Can I erase? All right. Now with free radical reactions, there are different steps that occur. The first step in a free radical reaction is initiation. That is the breakage of an element into radicals. That would be the definition of initiation. And we just saw this reaction again. We've seen this already, where this breaks apart like this, and this breaks apart like this. So we're going to get the radicals again like this. All right, so we title this as initiation.
And that says the breakage of an element into
Radicals. The breakage of an element into radicals. Yes.
Are there specific elements that?
Chlorine and bromine love to break apart. Fluorine and iodine. Fluorine does not like to, and iodine, they don't use it much in chemistry for radical.
Radicals are pretty much the
Yeah, only chlorine and bromine. So how many of you have heard of CFCs from propellants in like hairspray or some kind of a spray? So the reason why these compounds have been removed is they used to be very prevalent in spray cans, but now they've been banned. Because they go up to the ozone and ultraviolet light from the sun hits it, it forms a radical and then it destroys the ozone layer. It destroys the ozone molecule. And the less ozone we have in the air, the more ultraviolet light that comes to the earth, and that's what causes more cancer. So more and more people will get cancer wherever you have an ozone hole. And there's a big ozone hole above Australia. If you go online and look to see the ozone hole above Australia, you'll see it's very big hole, and a lot of the molecules accumulate in the area because all the winds push everything to that area, and then it destroys all the ozone in that area. So that's very bad for everything, because plants will get cancer, humans will get cancer, animals will get cancer. Everything gets cancer. So initiation, when we break apart the molecule into radicals. All right? Now let's look at a regular reaction and apply formation of radicals. All right? Let's do a simple reaction for you to see what's going to happen. This is the way that chemists functionalize an alkane. We get alkanes from petroleum distillates, from fossil fuels. So let's take a look at something like this. Let's look at something simple. Look to see what we're going to get here.
That is Z or 2?
2. Look to see the products we get when we react this. We have an alkane. When we take the chlorine gas and we put heat onto it, look to see where chlorine goes. It goes onto the tertiary carbon, and it goes onto the primary carbon. Let's put it here. Tertiary and primary carbon. What is the mechanism in which this reaction occurs? Let's take a look. We first start with initiation, just like we have seen. Breaks apart just like this. So we get radicals. All right. Then we get propagation. Propagation is when one radical reacts with a non-radical. That's the definition. One radical reacts with a non-radical. So I'm going to draw it right here. And we're going to put the hydrogen right out here, just like this. That's the tertiary carbon, hydrogen. All right. I'm going to take one of the radicals that I've made from the initiation step, and I'm going to draw it right here, just like this. And now what's going to happen is we're going to do homolytic cleavage to this bond right here, the carbon-hydrogen bond. All right. And we're going to start from the electrons on the radical. So look to see what we're going to do. We're going to form a new covalent bond between the chlorine and the electron closest to the atom, hydrogen. Just like this. So we're going to form a new covalent bond between hydrogen and chlorine, and the electron closest to carbon is going to go to carbon. Just like this. So now we get a radical on the carbon, plus we form HCl. Then I'm going to erase the initiation here. And another propagation propagation part 2. Propagation part 2, that's correct. We have the radical here. So this molecule here is now this molecule here. All right. I'm going to take a brand new chlorine, not a used one that reacted with lighter heat. You take a brand new chlorine, just like this, that did not react with lighter heat.
So you have to.
Yes,
You have to take the new chlorine.
brand new chlorine. Yes. A brand new chlorine is going to react with the radical on the carbon. What's the definition of propagation? One radical reacts with a non-radical. Do we have that in the next propagation step? Do we have a radical? Do we have a non-radical?
Yes.
This is propagation. Let's take a look. What's going to happen? We're going to form a new covalent bond between this carbon, and we have 2 electrons here in the chlorine bond. You take the chlorine electron closest to the chlorine that's going to react, just like this. And the other electron is going to go to the other chlorine. So what do we get? We get this. There's our product. That's our first product we showed the mechanism for, and is right here. All right. We can show the mechanism also for this compound here that's produced. Please tell me if everyone online has this already down so I can erase.
We're good over here.
All right. If we take the other molecule, if we take a brand new molecule, let's put this hydrogen here with the chlorine.
Oh, wait, what did you do?
I want to make this molecule now. See this molecule right here?
So you don't have to do initiation again?
Let's say initiation has already been done. Yeah. Initiation has already been done. Now let's continue with the propagation.
Yeah.
All right. What's going to happen now to this bond between carbon and hydrogen reacting with this chlorine radical? Take a look. All right. So now we get the radical here. Let's make it a little bit farther up so you could see it here. There. we get the radical now on the carbon. The second propagation step, I'm going to draw this right here just like this with my radical, and I'm going to take a brand new chlorine. And I'm going to react the radical with the electron closest to the chlorine that's going to react with the carbon. And now you see this molecule here that we have just made is this molecule right over here. Now look to see what's going on in all of these reactions. We make a non-radical plus we make another radical. This radical right here is able to react with more of the alkane that we originally had, so we can make more product. So free radical reaction is very fast. And it couldn't be infinite. Oh yeah. How many of you have used PVC pipe before? All right. Do you know how they make PVC pipe? Free radical reaction. How about ABS pipe? Free radical reaction.
Could you do it to like any of the other ones too, like the two other like little?
They're all equivalent. Let's look at the equivalence of this molecule. When we look at this molecule right here, the carbon in the center is equivalent to itself. The other carbons surrounding the central carbon are all equivalent to each other. So we can identify this as a blue carbon, this is a blue carbon, and this is a blue carbon. So it has 3 carbons that are equivalent to each other. So it only has 2 places for it to go. We can connect the halogen in the middle, and we can connect the halogen to either this carbon, or this carbon. They're all the same. Does not matter.
It doesn't matter which.
Does not matter.
The chlorine.
Yes, no.
Will there ever be a case where there's only one chlorine?
I don't understand. Can you explain again, please?
Because you have chlorine and 2, so you get the 2 chlorines that connect to each other. But if you get rid of it, it's just one. What do you do then?
All the halogens are diatomic in elemental state.
So it's always going to be 2.
So we always use elemental halogen to react in this reaction.
Is there ever going to be more than 2? So it's going to be like.
No,
3?
these do not react like that.
So it's
Only
only 2.
2.
Okay. So you're not going to put like 2Cl2 up there?
2Cl2. No, it does no. Oh, 2 moles?
Yeah,
If I put a 2 in front,
that's what I.
what does this mean?
2.
2 moles of the chlorine gas. That's what it means. What happens if I put 3 in front? What does that mean?
3 moles.
I have 3 moles.
But it doesn't like change like
It will.
any of that.
It will. It will. If I have 3 moles, we can say that 1 chlorine will go here, and we can install chlorine here, and we can install chlorine here or here. How many times? We can install it 3 times. So we could say 1, 2, 3. How about if we put excess here? That means we have more than enough chlorine. What do you think means? What do you think that means here? If we look at this, what do you think will happen? Look to see how it's going to be. We put chlorine here, here, there 3 of them are going to go on each carbon. You see what I've done?
That's how the middle one only gets 1 chlorine.
Because there's 3 carbons already bonded to it. So only 1 chlorine can go there because we can't break a carbon-carbon bond. We only break carbon-hydrogen bond.
So in this case, all we would do is just do all of these steps of propagation that many times.
Correct.
We probably wouldn't.
Correct. But I'm not going to have that on the exam.
Thank God.
I'm going to do monochlorination or monobromination.
Thank God. It was only 1.
1.
That's what I was worried about. Is
Only
like,
1.
You would only do this, and then like on the test, it would be like 4 Cl2, and I'd be like,
No.
oh my God, what?
No. Yes, Karen.
In what case does that happen? Like for what?
Do you know refrigerants that make stuff cold? Your air conditioning? All refrigerants are halogenated, except they use fluorine. The first ones that they used to use, like R12 and R22, they used to use that in refrigerant for cars and refrigerators and freezers. But all these chemicals were released into the atmosphere, and that's what started destroying the ozone layer. So they got rid of all chlorinated carbons, and now they put fluorine on there. When fluorine binds to carbon, ultraviolet light, the wavelength of ultraviolet light will not break the carbon-fluorine bond. It breaks the carbon-chlorine bond and the carbon-bromine bond, but it will not break the carbon-fluorine bond. So when you see, if any of you know anything about refrigerant, the 134A, R134A is all fluorinated. There's no chlorines on it. And that's what all the new cars are coming with now. So when they're all halogenated with fluorines, that's the new type of refrigerant. And the carbon molecule is different based on what type of refrigerant is used. So this is how they make refrigerants. If you took my Chem 152 class last semester, we went over these things when we were talking about ozone depletion. And we talked about the old refrigerants versus the new refrigerants. Any questions? Is everyone understanding free radical reactions?
So far, so good.
All right. That's all right.
This actually seems a lot easier than like the SN1, SN2.
Well, everyone loves free radical reactions because they think they're easier, and they are.
Oh, thank goodness. Thank goodness.
Now let's look at termination for this reaction.
Just kidding. It's more complex stuff.
Let's look at termination for this same reaction.
Just wait for it. You're just beginning.
Termination is when we have 2 radicals react with each other. To form non-radical. So all of the reactions we produced, we look back at what we wrote, and what radicals did we make? We made chlorine radical. So now we're going to take 2 chlorine radicals and react them with each other. This is a termination reaction. Termination. Two radicals react with each other to form a non-radical. We make our first non-radical. What other intermediates were seen in the mechanisms we drew before in propagation where we made a radical? I'll show you right here. We made this intermediate, which is a radical. And now let's combine it with a chlorine radical. Again, two radicals react with each other to form a non-radical. Notice we still make the same product, but the mechanism is incorrect. The reason why the mechanism is incorrect is because we need a propagation mechanism to make this product, not a termination mechanism.
To make that.
Yes, look to see what we have. We have a radical plus a radical, forming a non-radical. Is there anything else that is with these products to help the reaction continue? No, that's why we call it termination. The reaction wants to end now because nothing is there to continue the reaction and make it move forward. Meaning there are no radicals that are generated in the products to make it go forward. Let's look at another reaction. And I'm going to put it here. This is a side reaction. We take two of the intermediates of the radical carbon, and they react with each other. This is a termination. Look to see what's going to happen. Look to see what we make. We make now side product or side reaction, which in organic chemistry we consider junk. Because if you have to extract this, there's more stuff now you have to remove. Again, termination always generates a product, but no radical in the product to continue the reaction to move forward. All right. Any questions on this?
So this is kind of like what's happening on the side from the propagation.
Yep. This is because there's no more brand new chlorine to react with this radical.
But you could say that
So now it's,
propagation and termination is happening at the same time.
it all depends how much fresh reactants you have. If you have a lot of reactant, you're never going to have termination. But if our reactant is being depleted and we don't have any more, then now the reaction is going to start reacting with the intermediates that were made from propagation. And now we're going to get termination. Because the concentrations change and now reactants disappear, intermediates are made, they're going to react with each other to give us a terminated product.
Terminator project.
So we'll always end up with like a few different types of molecules.
Yep. Yes. Correct. How many of you have used crazy glue before? That's a free radical reaction. How about an epoxide?
Huh? What?
Have you used an epoxide?
Yeah. I use epoxy.
You may be using epoxy resin,
Yeah. Oh.
another type of free radical reaction.
Yeah.
How about styrofoam? Have you ever played with styrofoam before?
Oh,
That's a free radical reaction that forms that. All right?
And it makes that weird sound.
Yeah. It's like one of those oddly satisfying things.
So when we look from what we learned from SN1, SN2, E1, E2, we said that a carbocation forms a sp2 hybridized carbon. Carbocation is sp2 hybridized. A radical is the same hybridization. A radical carbon also has sp2 hybridized structure.
Why does it have a dash C?
sp2 hybridized carbon.
Oh.
So when we look at this molecule, or when we look at this intermediate, the radical looks like this, sp2 hybridized.
Looks like a bleak. Why? Yeah. Yeah.
All right. It has this structure. If it's a carbocation, we remove the radical, and we would just put the plus charge here instead.
So this one, the one with the radical,
The one with the radical is sp2 hybridized.
the carbocation.
Yes.
And then this one.
All right.
And then with the plus sign, it's a regular one.
No, with the plus sign is the carbocation.
Then what is it with the dot?
That's a radical.
Oh, I have it back.
All right.
What's that with the Y?
So if we look at carbocation stability, let's write this here.
It's the same.
Correct.
Torrential block?
Tertiary, secondary, primary.
Stability, tertiary, secondary, primary, methyl.
That's for the radical stability?
Yes, and carbocation, because they have both the same hybridization. sp2 hybridized. All right. Can I erase? All right. Now let's take a look at do you remember from resonance when we had conjugated pi system? You remember from resonance when you need a conjugated pi system?
Yeah.
Let's go over that. Double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond. Do you remember conjugated pi system?
More or less.
Like the which one is the
Correct.
the sigma bond?
Yes, that's correct. What is the hybridization of all of these carbons?
Two.
Everything here is sp2. That's correct. Everything here is sp2. We can look at any one of these, and it's going to be sp2, right? All right. They're all sp2. We just learned that the carbocation and the radical are both sp2. So we can have resonance if a conjugated pi system is next to a radical. Just as if a conjugated pi system is next to a carbocation. We can have resonance. Yes.
Like a what? I'm not even with it.
No.
Okay.
So let's do over something that we've seen before. Let's do the carbocation first, and then we're going to do the radical here. We've seen all of these before from the first exam. When we have the carbocation, what do we do?
Right. Wait, can you say that again?
How would we move the electrons in a carbocation when it's conjugated to a double bond?
So you move them with a double pointed arrow.
Like this.
And then the carbocation takes the spot.
Correct. We get the resonance structure with the carbocation at the bottom carbon. If we have a radical, what do we do?
You move it to the
Let's put the double bond here. I forgot to put a double bond. Here it is.
So fish hook arrow to the bottom.
Fish hook to the bottom, like this.
And a fish hook to the top.
And a fish hook to the top. And then this goes
The radical
here.
fish hook to the other. To the bottom.
correct. Exactly correct. And what do we get?
An X standing on a dot.
We get this.
X standing on a dot.
All right. Radical moves down right there. All right. Is everyone understanding how this carbocation and the radical move? We're interested in seeing the we're interested in the radical because this is a free radical reaction chapter. So let's do a reaction, a free radical that's conjugated to double bond. And let's do something simple here.
Roar.
Let's take a look at this reaction. All right. Here we have HCl, hydrochloric acid. And we have a peroxide down here. We have a peroxide. So what does the R stand for? The R can stand for hydrogen or carbon. So this can be hydrogen peroxide, what you buy at the pharmacy store. Yep. Hydrogen peroxide. All right. So I'm going to show the first reaction right here. Initiation. And let's put this heat or light here with initiation. Initiation, we first take the peroxide molecule. Notice how we have two oxygens next to each other. What type of reaction do you think is going to occur between these two atoms?
Propagation.
Initiation. You see how we have two atoms that are the same?
The oxygens are gonna split.
Correct. The oxygens are going to split.
Radicals.
Just like the chlorine split.
The homolytic.
Homolytic. Look to see. We take these electrons from the bond, we split in half, homolytic cleavage, and we form hydroxide radicals. All right.
So how come that homo that typically means together, it means separate? No,
Homo means
never mind. Is it?
the same kind.
Yeah.
The
What
same
is it?
atoms split apart from each other.
Oh. Okay. Because they're the same.
They're the same atoms, they split apart from each other.
Okay.
So initiation again, formation of radicals. Now let's do propagation. We're first going to take the hydroxide radical that we just made, and we're going to react it with HCl. Okay? Hydroxide radical is going to react with the hydrogen of the acidic hydrochloric acid, just like this. Look to see what we're going to make. We make an alcohol, plus we make chlorine radical.
Or it could be water.
It could be water too. If it was hydrogen peroxide, it would be making water. Yes, that's correct. Very good. Now look to see what we make here. If this R was an H, if I erase it, if this R was an H, it was hydroxide radical, what would the product be here?
Water.
Water.
That's an acid-base reaction. Hydroxide and HCl.
Yeah, but it's not an anion. It's a radical reaction. It's not that type of reaction.
Gotcha.
Be careful. All right. So look to see what we make here. You see our radical right here? This is now what's going to react. All right. I'm going to erase this. And I'm going to take this and put it right here. Propagation 2. Let's put, we want to react the double bond now.
Is it okay to flip it around?
Of course, you can flip it around. Notice in the product, the double bond is gone. See that? See how the double bond is gone? That means we reacted the double bond here. Let's take a look. We're going to take the radical that's closest to the double bond that's least substituted, because the intermediate has a radical that's more substituted. Look to see what's going to happen. we form a more stable radical. See how it's secondary?
Doesn't matter where you go down, you know, connecting from Cl, you go down and then up. Doesn't matter if it would have went up and then down.
No, does not matter.
Okay, they always go up.
Then we take a brand new HCl and we react this to give us this product.
Do you not have to write the hydrogen at that point then?
No,
Okay.
So what is it like this? Like,
no, only if it is a heteroatom will we add it. If it's hydrogen, it just disappears. We just sew the carbon skeleton and any heteroatoms, we install them in. All right. So if we identify this reaction, which we can do for all of these reactions, this goes from an alkene to an alkyl halide. And an alkyl halide means an alkyl group. When we have the word alkyl, instead of alkane, we take the ANE off and we install a YL. Alkyl means it's a carbon group. That's an alkane.
Mr. Hollow,
Yes.
just to be clear on this propagation that you put at the bottom, right there where you had your HCl there at the last part, yeah. So one radical from the bond between the H and the Cl met with the radical from there. So what happens to that bond to the H? They just gone, the bond and the H together?
See this bond right here?
Yeah, yeah.
One electron
Right.
is going to form a bond with this radical
Right.
here on the carbon.
Right.
And the electron closest to chlorine is going to go with the chlorine. So look to see
Right.
where it is here.
All right. So then we don't have to write the bond with the electron at all then, right?
No.
Okay.
There's a hydrogen here. You have to understand that's the one we
You're right.
We do not need to write it.
Okay, cool. We just want to make sure so we don't have to.
So can we put that so it's not so confusing?
Hold on. Say that again.
Can we write that so it's not confusing or no?
Yeah, you can write it if you like. That's totally fine.
for the families here, hydrogen is here, so we know that.
Cool. Thank you.
You're welcome. All right. So back to the naming. The alkane changes to the word alkyl. We remove ANE if there's a substituent. And what is that substituent? A halide. So now we say alkyl halide. That's how we get this name. All right. And now look to see how this is being added. The chlorine, let's look at this alkene. All right. Which side of the alkene is more substituted?
The right side.
This side here. That's correct. The right side is, no, this is less substituted, this is more substituted.
Oh, yeah.
This is less, this is more. Notice where the chlorine is going. It's going to the less substituted side. All right? There's a special name for this I want you to remember because we'll go through it when we get to the next chapter. This is anti-Markovnikov. Anti-Markovnikov. A Russian chemist
Would have never guessed.
named this after his name.
Markovnikov.
Anti-Markovnikov says you add the hydrogen to the more substituted side, which we did. Hydrogen is to the more substituted side. And we add the heteroatom to the less substituted side. That's anti-Markovnikov. If it's not anti and it's just Markovnikov, it says that we add the hydrogen to the less substituted side and the heteroatom to the more substituted side. It's opposite. So if I draw regular Markovnikov, here's what it would look like.
The CO would be on that.
This is what it would look like here.
In place of the hydrogen.
This is Markovnikov. You see where chlorine is?
Yeah.
It's on the more substituted carbon. Whereas anti-Markovnikov on the less substituted carbon. So anti-Markovnikov. For free radical reaction, anti-Markovnikov is the only product you're going to make. Because the intermediate generated is more stable when it's secondary. If you want to generate a radical here, it would be primary. If you do a radical reaction. So it's not favored. Does everyone understand that? All right. Yes.
So for the exam, did you include chapter 10, 5?
No.
Just 10?
I put it in. If you look to see, all I did was remove 5, and then we're going to do. I posted the new syllabus online, and I changed Schoology. So you'll see. So we're going to go through chapter 10, which is today, and then we're going to do chapter 8 next week, and then we're going to do chapter 9 the week after. So we're doing free radicals, which is taking first one we learned, we take an alkane and we turn it into an alkyl halide. And now this is showing an alkene going to an alkyl halide. I'm going to erase this and look back and name the type of reaction we just did right before this. The best way to study for organic chemistry, now that we're getting very specific reactions, is to put alkane goes to alkyl halide, just like this. And then you will put a general reaction. This is what we just had. Alkane goes to alkyl halide, just like this. That's a reaction we did before the one we just did. So title it, alkane goes to alkyl halide, just like that. All right. Can I erase? Everyone online?
A little bit, wait.
What did happen?
Almost there, almost there.
Okay.
Okay, we're good.
All right. Now let's look at bromine. Let's look at something more complex. Let's look at this molecule here. Where do you think, well, let's identify all the type of carbons. What kind of carbon is this? Primary. What kind of carbon is this?
Primary.
It's also primary. What kind of carbon is this?
Tertiary.
Tertiary. How about this carbon?
Secondary.
And how about the one at the end?
Primary.
Correct. Bromine is selective. It wants to go to the most substituted carbon. Where do you think all of the product is going to form? Only on tertiary. So where we saw chlorine reacting with the carbon, and it would go to all positions, let's show comparison here. Look to see what's going to happen if we put chlorine here. All right. Let's put it here first.
Did you put bromine?
This is what we're going to get if we use chlorine on this molecule. Who wants to separate these? If we were mixing, if we were doing an extraction, and if I say, all right, we just did a product, I want you to separate the products. Which reaction would you prefer to have done?
Bromine.
Bromine. Exactly. This is the problem with chlorination. It goes everywhere. With bromine, it just goes to the most substituted carbon.
So even though the tertiary is preferred on the chlorine,
It gives you a mixture of everything, yeah.
go everything where bromine is more.
Yeah. So even though this would be, let's say like this, that's how this one would be. How would these be? This would be like 60%. This would be 30%. And then this would be 5. And then another 5. It would be like that. So it's a big mess. It's not good for synthesis. So bromination is a lot better.
So bromine can, if there were only one molecule with a tertiary and primary,
It looks like it.
then go to tertiary.
It will only go to tertiary. It won't even go to
And if
primary.
there was only one, which would be a primary, it would work or it would not.
It will go to primary if that's the only one that's on there. So Rhett was saying, if we have a bromination and just a primary, bromine will only go on the primary, nowhere else, because there's nothing else to go to. But if it has a selection to go to one, if there's a different type of carbons on the molecule, bromine is going to go to the most substituted one. That's it.
And chloride doesn't matter then? I mean, would it go to any?
It wants to go to a mixture.
Okay.
You can't see these, but I could see right here. This one would have been like 5%, and this would have been 5%.
So on the test for the chlorine one, you would want us to show
All of them.
a representation, not the whole, each hydrogen, but the
Yeah,
whole.
just, yeah.
Okay.
Now let's look at these molecules that I have done. Are any of these carbons that the chlorine have bonded to, are they stereocenters? Look at the bromine first. Is that a stereocenter? No, stereocenter. It has two methyl groups that are the same. Then we have an ethyl group that comes off in bromine. Where's 1, 2, 3, and 4? You'll get stuck on 3 and 4. That's the problem. They're both the same. It's not a stereocenter. How about this? Is this a stereocenter? Is this a stereocenter? Look closely, please.
That one looks like it.
Guess where we have a stereocenter?
Right there.
Right here. So, we learned that a radical intermediate is the same as a carbocation intermediate. So when the radical reacts, it can attack from the top or the bottom of the radical. So we're going to get a racemic mixture of this compound. We're identified here. This here is a stereocenter. So what do you think it's going to look like? We have wedge up, wedge down here. So I'm going to put this like this.
And the dash.
And I'm going to put the dashes right next to it. Correct. Stereocenter. Racemic mixture of these here. See that? How about this? Is this a stereocenter? No. How about this one? Is this a stereocenter? No. So we only have one molecule that gives a stereocenter. So we're going to get racemic of that molecule. All right. What? All right, let's take a little break. So in the in your book, they have a lot of calculations of calculating delta H. I'm not going to test you on that. And then they talk about on page 357, they talk about rate of abstraction. I'm not going to test you on that either. They used to talk about that on the MCAT, where you have to learn it. Now they've excluded it. So if it's not on MCAT, I'm not going to go over it. All right. Does anyone have any questions of what free radicals are or mechanisms? All right. What is it?
So you had an example with HCl and a peroxide.
Correct.
So how aware of those two different, what you had HBr, and what would be this, like, is there differences in the solution?
Oh, if we use HBr, we're going to learn that next on the next chapter.
Like if there was a,
It's ionic.
it was HBr in water, with that
Totally different. We're going to learn that. So Rhett says if we have HBr in water, what's going to happen instead of using a peroxide? We're going to learn that in chapter 8.
So shouldn't be aware of the polyproduct or
So I don't want to get that, and I don't want to confuse that with the free radical chapter, because this chapter kind of integrates it. But what I'm trying to do is make it separate, and I'll bring back the radical and show you when we do the Markovnikov addition to the alkene. All right?
You know the Mega Millions is at 1.6 billion, sorry.
Yeah, you may want to buy a lottery ticket because it's 1.6 billion.
Yeah, but they said it was like 1 in like 200
It's
something thousand.
it's very low chance.
Yeah.
People have been already playing and they didn't even win anything. So it shows you the ratio to get it is super tiny.
It was like 1 to a million something. And I was like, what the heck?
Last time the Powerball was this high, 3 people won. And you each walked away with 385 million after taxes. That's with 3 people winning.
Yeah.
After taxes.
Yep. All right. So that's free radical chapter. We will go over other free radicals, but in this particular case, what's in this chapter is what I want to go over. So I've already lectured on it. You should be able to do all the problems from this chapter. Now I want to go over chromatography, which is for the lab that is this Wednesday and next Wednesday. Yeah. So I need an hour to do this, to explain everything.
All right, well, you can have like 40 minutes.
All right. So first of all, I changed, if you look online, I did change the lab. I put in a new, I attached a PDF file of a whole organic chemistry lab book on Schoology, and I posted what pages I want you to print out from that PDF file of the book. All right?
Bring to us.
So what we're going to be doing is using, we're going to be doing TLC. So let's explain what TLC is. Let's write it up on the board.
It's a TV show.
TLC is not a TV station, and it's not a TV show.
What about a band?
No, it's not a band either.
That's a cool band name,
It's-
though.
It stands for thin layer chromatography.
Roll.
Yeah, it's not Beyonce's band, TLC. I know, but it's not. Thin layer chromatography, TLC. So this is a separation technique. And is used for purification. Oh. I am. Like that?
Yep.
All right, technique. It's used for purification. You know, we can, well, I have this. Let's look at it. Let's look at chromatography first, and then I'll integrate TLC. So just change this for chromatography.
Is it the same thing?
Yeah. It's still the same thing, just chromatography.
Not thin layer.
We're going to bring in thin layer after I explain what chromatography is. So it's a separation technique, and it's used for purification. It can also be used to identify reaction progress. And it has a moving phase and a stationary phase. So the moving phase is a solvent. And the stationary phase is either silica or alumina gel. They call it a gel. But it is a solid. Let's look to see what is silica. It is SiO2.
Mr. Hollow,
Yes, sir.
we're still going to be doing the pre-lab for this one then, right?
Or are we just printing it out?
Well, we're just printing it out.
Just a printout.
Yeah, you will see the print. You will see the pre-lab. You will do the pre-lab. This book that I posted on Schoology will have all information for you to write your pre-lab with.
Okay. When you posted the book, you posted that 300 and something pages on it, but you only want us to print those pages that you wrote down, right?
Yes.
Okay.
Yep. Don't print out the whole. There's 300 and something pages. Don't print all 300 and something. Just focus on the few pages that I told you to print.
It was like 117 through 128.
117 through 128.
Yeah, 117 and 128. Yes.
Okay.
Oh, 117 and 128?
Through
117
Through 120.
Okay.
You don't even need to print it because
Through and and.
Through.
Two totally
Through.
different things.
Through.
117 through 128.
It's listed on Schoology and listed on the syllabus that I post. So let's look at silica and alumina. Silica is SiO2 and alumina is Al2O3. These both have oxygens. These molecules both have oxygens. You see that? All right. Can I erase? There's more I want to put down. Both phases, which is the mobile phase and stationary phase, what goes on there is a partitioning. There is a partitioning between the mobile phase and the stationary phase. Meaning, when the compound moves through this phase, understand the compound is going to be dissolved in a solvent, which is what we call a mobile phase. As the solvent moves, depending on the polarity of the molecule that's dissolved in it, the molecule that's dissolved in it is going to bind more to either phase that it is most similar to. Remember how we talk about like dissolves like in general chem? Where nonpolar dissolves nonpolar and polar dissolves polar, but when you take polar and nonpolar, it forms a heterogeneous mixture. So depending on the polarity of the molecule that's dissolved in the solvent, it's going to select to stay in the solvent or it's going to bind to the stationary phase. Does that make sense to you? So it's both based on the polarity of the molecule. So we would say it is solubility versus solubility versus adsorptivity. It's not absorb, it's adsorb. It's not actually being absorbed by the phase, it's just sticking to the phase.
Adsorbed.
So we call it adsorbed. It's not absorbed like a paper towel will absorb water. It's not like that.
You just so absorbed in the ad to show.
Correct. It's just being, it's a word that's primarily used in organic chemistry because you've probably never heard of this word before.
No.
So when we say solubility, that means in the solute, in the solvent. And when we say adsorb, that means in the solid phase, to the solid phase.
In the solid phase or to the solid phase?
To the solid phase, of the solid phase I have. Yeah. Let's put that. Sticks to. Sticks to solid phase. That's a good word. I like it. That's what it's doing. It's sticking. It's adhering to the solid phase by intermolecular forces, like hydrogen bonding, van der Waals, dipole-dipole, induced dipole, stuff like that. Primarily hydrogen bonding. Because the stationary phase has oxygens, and if your molecule has OH groups, then you can do some type of hydrogen bonding there. All right? Now let's do TLC. Can I erase?
Yes.
So thin layer chromatography, also known as TLC, is a qualitative separation. What does qualitative mean?
Subjective.
Let's put it in different words than just subjective. In simpler words, is it a large quantity or a little quantity? Tiny amount or a large amount? It's a tiny amount.
Quantity over quality.
This is a tiny amount.
Yeah.
One little drop. One drop of the whole reaction is what we're going to test. So this is tiny amounts. Tiny amount is what this will test. Small quantity. All right. I want to draw this right here. And that's the type of question that they will ask you on the MCAT, just to let you know. What is TLC? Quantitative. It's not quantitative. Yeah, qualitative, not quantitative. Quantitative is a large quantity, and that's what's going to be for column chromatography when we do it next week. So let's take a look at the sheet, the TLC plate that we're going to be using. TLC plate's going to look like this. It's going to be a piece of plastic sheet, and it's going to have the alumina or silica on it. What you're going to do with your pencil, please bring your pencil when we do TLC on Wednesday. All right? Down at the bottom, you want this distance here. Let's put a little line here like this. You want to put a very light pencil line on the bottom of the sheet. You don't want to dig into it because it's very easy to gouge it. You don't want to gouge it. You want to lightly draw with your pencil over it. All right? And you want this to be like 2 or 3 millimeters. Let me see, just a tiny amount. Millimeters. Make it 3 or 4. Let's do 3 or 4. 3 or 4 millimeters from the bottom. All right. And what you're going to do, you're going to have a jar just like this, glass jar. And you're going to put a solvent in at the bottom, just so the solvent is below this line. You want the solvent below this line. Does that make sense? If you want to go up a little bit higher, you can. We could change it. Let's say 5 millimeter. Fine. Change it to 5 millimeter.
That's the final answer.
Yeah.
No more changing.
All right. No more changing.
My whiteout.
Let's put 5 millimeter. All right. The objective is to put the solvent in the jar lower than this line. If this line gets submerged when you put the solvent in, the molecules that you're going to put on this line will not move up. And that's what our goal is, to separate the molecules. And it's going to be done by capillary action.
The little tube.
Capillary action
I've done this before too.
is going to allow for the separation of molecules of the solvent moving up the stationary phase. So there will be, do you remember the capillary tubes we used for melting point?
Yeah.
All right. You're going to be using some that are very similar to that, except it's open on both sides. It's not rounded off on one end and then open at the other. It's going to be open on both ends. All right. And what you will do, you're going to, just like you touched the capillary tube to the powder and you push it into the tube, you're going to do the same thing with, we're going to use tomato paste. You can use pumpkin paste, you can use spinach. There's a whole bunch of different things we can do in natural chemistry.
And I feel like, are you bringing those things in, or is it-
We're going to have tomato paste.
Why not pumpkin? Pumpkin's much more fitting to the season.
I know, but he wants to do,
It smells better.
all right, we'll see what we can do.
All right.
We'll see what we
I'm
can do.
up for my own.
I'll bring my own pumpkin paste.
So whether you use pumpkin or tomato or spinach or any kind of something that has color, that's what our objective is. We're going to use some kind of natural compound. you're going to touch that little tiny capillary tube onto the, we're going to have it already dissolved in a liquid, actually. All right, we'll have it dissolved in a liquid, and all you're going to do is touch the capillary tube to the liquid, and some of it's going to run up inside of the capillary tube. And then what you're going to do with the capillary tube, you're going to go right to this line, and you're going to be able to, let's say if this is the tube, you're going to go with the tube, the side that has the color that it was just injected in from the bottom, and you're going to go, and I want you to just touch it very quick like this. And then, same place, touch it again, touch it again, touch it again, until you see a dot of color there. It may need only once, because if we're going to use pumpkin, well, the red is darker than the pumpkin, but depends how strong the color is going to be. You may need to touch it once. But if the color is too light, touch it again, touch it again. If you let it sit, if you put the capillary tube and let it sit there, all the liquid's going to go out and your dot is going to be very large. The objective is to have the dot as tiny as you can have it. The tiniest dot. Tiny dot.
No liquid.
The liquid is going to evaporate. Because we're going to be using a solvent that's organic. So if you touch it fast, on the line, touch it, pull it off. Touch it, pull it off. You put it on the same dot that you originally did, you will stay a tiny dot. But if you hold it there, you'll get a large dot. You want it to be tiny.
So we just want to lightly touch the surface. We don't want to penetrate the gel.
Correct. You want to touch the surface and not penetrate the gel, or you're going to have to throw that plate away and start off with a new one. And they're expensive. So we want to save them. Do it correctly. All right? All right.
All right.
Once we put, and you can do 2 or 3 there, that's totally fine. You could probably put 3 dots, 1 here, 1 here, 1 here. If you can do it very well, you could squeeze 4 in here. If you do it correctly, you could put 4 on one sheet.
4 dots.
Yeah. But you have to mark to see where they're going to go on the sheet. All right? Then you'll take this sheet, after you have put spots on it, you're going to put it into the chamber that already has solvent, and you're going to close the lid on it. And what you're going to see is the solvent that you put into the bottom is going to move up the TLC plate by capillary action. And what's going to do, it's going to separate the different molecules based on polarity. So even though you see the tomato paste as red, when you see it separated out on TLC, you may see a red dot, an orange dot, a green dot, a yellow dot, and everything's going to separate on that going up the TLC plate. So you're going to see the other, what we call chromophores, that come off of this mixture in the lycopene paste or in the pumpkin paste. So you'll see all the different colors that come off of there.
I think I remember doing this in like microbiology.
Yeah, you do it in micro.
It was a couple of years ago, so I don't really remember. But
Once the solvent, when the solvent almost reaches the top, we call this the solvent front. Let's put a line here. And this is called the solvent front. Once it reaches almost the top, and you'll be able to see it, even though the solvent is clear, you'll see it wet versus dry. You'll be able to see it. You'll grab it with the tweezers, you'll pull it out from the top, and as soon as you lay it down on paper towel, you're going to take your pencil and you're going to draw a line right where you see the solvent line of wet to dry.
very clear lately.
Very lightly. Because what's going to happen is the solvent is going to evaporate and you will not see it anymore. So let's give you the example, what it's going to be. Let's just do this one here. Let's say I get a red dot and a black dot and a blue dot. Okay, I wish I had more colors. So let's say we get 3 colors off of this TLC. What we're going to do is take your pencil very lightly and you're going to circle the dot, just like this, circle the dot, and then you're going to identify the center of that dot. Identify the center of the dot. The reason why I tell you to circle the dot, there may be some colors that are photoreactive and they may disappear after a while. So if it disappears, you may not know exactly where that dot was. All right. Now that we have determined the center of each dot, you want to calculate the distance between the solvent front and the original line. That's the total distance. Total distance from beginning to end. Then you want to measure the distance between the center of each dot to the original line. Just like that. All right. And let's give just some numbers here. Let's say the total distance was 50 millimeters. All right, 50 millimeters for the total distance. And then I have on the first red dot, let's say that I have 15 millimeters. And then I have 25 millimeters. And then I have 30 millimeters. Now I'm able to calculate the ratio. The ratio is going to be calculated by the number it moved up versus the total number. So we can do 15 over the 50. And you're going to get a point number value. So this becomes the RF value. This is, let's write it here, distance traveled by solute over total distance traveled by solvent. Solute over solvent. That's the RF value. All right. So the type of solvents that we're going to be using include petroleum ether, acetone, methanol, three different kinds of solvents. The objective of this experiment is to get the best separation of the compounds. Because this, what we're going to determine is whatever solvent is the best is going to allow us to do next week's lab, which is column chromatography for large scale, and we're going to be able to isolate each compound individually based on what solvent.
And there's all compounds either going to be tomato paste or pumpkin.
Yeah, we're going to see which one. Yeah. So put down, I don't know what we're going to be using. We may be using pumpkin paste or tomato paste. All right.
So we're separating the compounds in either the pumpkin or tomato paste using the solvents, and this is to see the best solvent to separate those compounds.
Correct. Our objective is to separate all the compounds using one solvent, and maybe a mixture of solvents too. We may have to mix 50-50 petroleum ether with methanol to get the best separation. We may have to mix methanol with acetone 50-50 to get the best separation. It may give us the best separation if we mix all three. But this experiment is going to help us determine what solvent we need for next week's experiment when we do column chromatography, which is quantitative, large scale. And we'll be able to isolate each compound individually in the Erlenmeyer's lab. All right. This is a cool experiment.
I remember it was cool when we did it in Ohio.
It's going to be very cool here. Does anyone have any questions for me? I want you to put ethanol here too. Let's add ethanol, or let's add, forget ethanol, let's do isopropyl. Isopropanol. Isopropyl alcohol. A little bit more nonpolar than methanol.
So are we going to do one plate for each one, or are we going to have separate?
We will have, everyone will just, we'll have different groups, and we'll have two, one group will run two, the other group will run two, and see which one is the best. Isn't that cool? And then you'll see their RF value, which one's the best. But just based on their separation, you don't have to see that, you don't have to calculate RF value, you just see which one, where they separated the best. So let me give you an example, and you tell me which one you think is the best. Can I erase? Is everyone understanding so far?
Yes.
All right.
So the radio, the better the RF.
Yeah. So let's give you an example, and you tell me what plate looks the best, okay?
Go on, save on it.
I should have kept this one here. out of these 3 plates that I've drawn up here, which solvent best separates the 3 compounds?
The third one.
The third one. Correct. So then, if you see the third one, how it separated all 3 compounds very nicely, we're able to do a large scale of this and get the same separation using the same solvent in a large scale separator, which is column chromatography. But if we do column chromatography using this solvent or using this solvent, we're not going to get good separation. With this, everything's going to come out at the same time. So that's not good. We're going to get one good separation here, but these 2 are going to come out at the same time. So that's not good. Our objective is to get individual compounds to come out at different times. So we're able to isolate each one of them. Before you go, I want you to understand column chromatography because I want to lecture on it now before you go. This is for the week after. So after doing TLC and determining what is the best solvent to separate out the compounds from either pumpkin or tomato, we will do column chromatography. Column chromatography is also known as CC. Yep. Column chromatography is for quantitative. Separation. That means a large amount. This is how they do it in industry. If they want to separate a specific compound from a whole mixture, they do a TLC to see what solvent is best to do a separation of all the compounds that give different colors. And then they put a whole bunch of the compound, or they take a whole bunch of the natural compound and they put it into a column chromatography setup. And then they look for that color and they take it all out. And then they evaporate the solvent and now they have that pure compound. So this is used to separate large or small quantities of 2 or more compounds in a mixture. This is powered by gravity. If you write in your paper for TLC, it's powered by capillary action. This one is powered by gravity. Can I erase? Again, this has 2 phases. You have the mobile phase. And you have the stationary phase. So the mobile phase is inert, which means it does not react with the compounds. So it can be a pure solvent or it can be a mixture of solvents, like 50-50 ethanol and acetone, or 50-50 of petroleum ether and isopropanol. Something like that, where you can have a mixture of different solvents to make up the mobile phase. The mobile phase is also known as the elutant. So if you hear me say that word, and when you read it inside the theory of the book, they talk about the elutant. That means the liquid that comes out from the bottom. That's going to separate everything. All right. So that's the mobile phase. So it can be, let's just put this down. It could be 100% hexane, or it could be 100% acetone. These would be of the pure solvents. Or it could be, if it was a mixture, 50% hexane, 50% acetone. That would be your mixture mobile phase. All right. How about the other phase? Stationary phase. This is going to be powdered silica or alumina. Powdered silica or alumina?
Powdered or powdered?
Oh, powdered, sorry. Powdered. Powder. Let's put here powder. Powdered, like powder.
Is the alumina gel or is it powdered?
It's powder.
Okay.
Once you put the solvent in, it'll turn into a gel. And this is the adsorbent. Adsorbent is the stationary phase. And this is based on like dissolves like. if the solvent is the same polarity as the liquid compounds, which is the solute, they will move fastest down the column. I won't erase it yet. If the solvent has opposite polarity as the liquid compounds in the solute, they will move slowest down the column. Okay. Can I erase?
Just
When the solvent elutes, they can be tested by TLC or distilled to obtain pure compound. Now, before you go, I want to discuss with you how you're going to fill the column up with the silica or alumina gel we have. It's powder at first.
better if you cover this next week because I don't want to forget for the next.
All right, we'll cover it. We'll cover it in the lab when you get here.
I don't want to forget with the next couple days.
All right. This is all the theory you could put in there with your introductory stuff. All right.
So do we do the pre-lab too? Or is it on that sheet?
Yeah, it's on the sheet.
So we don't
You're
have
gonna
to
do
put
the-
it in our notebook.
I want you to put it in your notebooks, but you're going to use the information from that book and you're going to apply it to your notebook.
Okay.
There's some people, you know.
So yeah.
We'll do
so
You
the
still have to do pre-lab.
But don't do any post-docs.
The only time you won't have to do pre-lab is
We die.
When you say so.
when we finish all the labs. Yes, sir.
Okay. Bye guys.
See ya.